This first question asks us to calculate the molarity of the perchloric acid solution. To do this, we need a value that has moles of solute on the top and liters of solution on the bottom. The two values that we're given in the problem is the percent mass, which gives us mass of solute per mass of solution, and the density, which gives us the mass of solution per volume of solution. The better starting point here is going to be the percent mass because we have a ratio of solute per solution, which we have here, solute per solution, instead of solution per solution. So I'm going to start with the percent mass. I'll convert the grams of solute into moles of solute by knowing the molar mass of my perchloric acid, and then I'll convert the grams of solution into liters of solution using the density value. Focusing on the units, I can see that I have eliminated grams of solute and I'm in mole of solute. And I've eliminated grams of solution by converting it to milliliters of solution and then milliliters of solution to get into liter solution. So my final units here are moles of solute per liter of solution, which is molarity. I calculate my answer and I find it to be 10.2 mole of perchloric acid for every liter of solution, which is my molarity. The pH of an aqueous solution is calculated by finding the negative log of the hydronium ion concentration. And by concentration, we mean molarity. Now you may be asking yourself, how can I find the hydronium ion concentration when all I have is the acid concentration? Well, this is quite simple if you know what acids do when you have them in water. Any acid, which we've drawn here as a hydrogen with an anion, this can be any anion of a strong acid, any acid will lose its hydrogen proton to water, making hydronium. And then the anion portion of the acid just becomes an aqueous anion floating around in the solution. So if you know the molarity of your acid, you actually know the molarity of your hydronium ion just by knowing this equation here. For our specific acid, perchloric acid, it is a 1-to-1 ratio of the perchloric acid that you put in the water to the hydronium ions in that water. So if I know that my molarity of my perchloric acid is 10.2 molar, what's going to happen is that's going to end up with 10.2 molar hydronium ions. So that is what I'm taking the negative log of. And now we simply put that into the calculator. The negative log of 10.2 molar hydronium ions is negative 1.01, which is an incredibly acidic solution, which makes sense because 10.2 molar acid is a very, very concentrated acid. Moving along, let's see if we can figure out what the molality of this perchloric acid solution is. Recall that the molality is a moles of solute per kilogram of solvent. If you remember from above, we were given a gram of solute per gram of solution calculation called the percent mass, and a gram of solution per milliliter of solution value in the density. So how can we get to a moles of solute per kilogram of solvent? Well, once again, I'm going to go with the percent mass, but I'm going to change it around a little bit. If I have 61.4 grams of solute for every 100 grams of solution, well, what makes up the other portion of that 100 is the solvent. So while yes, it is true to say that it is 61.4 grams of solute for every 100 grams of solution, it's also true to say that it is 61.4 grams of solute per every 38.6 grams of solvent, because solute plus solvent equals the mass of the solution. Now that we have a ratio of grams of solute per grams of solvent, it's very easy to get to moles of solute per kilogram of solvent using all the same conversions we just did above. So from above, I'm going to take the 1 mole of perchloric acid is 100.46 grams of perchloric acid, and I'm going to convert my grams of solute into mole of solute just like I did before. But now I don't want to get to a volume of a solution. I want to get to kilograms of solvent. So that's an easy one step. 1,000 grams of solvent equals 1 kilogram of solvent. Focusing on my units, I can see that now I'm in the unit of mole of solute per kilogram of solvent, which is the unit of molality. Now I just calculate, and I get a value of 15.8 moles of my solute per chloric acid per every 1 kilogram of solvent. Notice that even though molality and molarity seem very similar, we get very different results because one is moles per liter of the entire solution, where the other is moles per kilogram of only the solvent. One of the main reasons why I introduced molality to you is because there's some cool properties that are the result of calculations that use molality, one of which is freezing point depression. Our equation for freezing point depression is the change in the temperature of the freezing point is equal to this Van't Hoff factor, which is just how many particles the solute breaks up to when dissolved in water, Kf, which is a constant for a given solvent, and then the molality of the solution. For us, Ri, the Van't Hoff factor, is 2 because when you dissolve perchloric acid in solution, it breaks up into 2 particles, an H plus particle and a perchlorate ion, a ClO4 minus. Since there's 2 ions, we get a value of 2. Our Kf value for our solvent water is negative 1.86 degrees Celsius per mole, and that will always be given to you. It does change when you change the solvent, but most of the time for us it's going to be water. And then lastly, our molality is 15.8 moles per kilogram, which we just found above. Now it's simply just plugging these numbers in and calculating the change in the freezing point of the water solution. By calculating, we find that the freezing point will be lowered by 58.8 degrees Celsius. And since water's freezing point is 0 degrees Celsius, that means our new freezing point is negative 58.8 degrees Celsius. Note that if we had a different solvent where the freezing point was not 0, we would have to just take that solvent's freezing point and decrease the freezing point by 58.8 degrees Celsius from whatever it was originally. Now in this next question, a student takes 50 milliliters of this super concentrated perchloric acid solution and adds it to a beaker, then adds 450 milliliters of pure deionized water, so that the total volume of this new solution is going to be 500 milliliters. And the question asks, well, what is the molarity of this dilute solution? Here we're going to use our C1 times B1 equals C2 times B2 dilution equation, where our initial concentration, C1, was 10.2 molar, and our initial volume, how much of that concentrated solution we started with, is 50 milliliters. We want to know what our final concentration is, that's C2, and we know that the final volume of the entire solution is 500 milliliters because it's the 50 milliliters of concentrated solution plus the 450 milliliters of water that we added to the beaker. We set up our equation, we solve for x, and we find that x is 1.02 molar. To calculate the pH, we're going to take the negative log of the hydronium ion solution of this new dilute solution. Same thing as before, we just take the molarity of perchloric acid because the molarity of the perchloric acid will be the molarity of the hydronium ion solution. The negative log of 1.01 is pretty much 0. It's going to be technically negative 0.0086, and that makes sense because the log 10 of 1 is 0. So we're just slightly above 1, so we're just slightly below 0. The student then makes a second solution by adding 30.52 grams of strontium hydroxide to 300 grams of water, resulting in a solution that has a density of 1.13 grams per milliliter. And we want to know what the molarity is. So again, we need to get a value that is moles of solute per liter of solution. So we can find the moles of solute by using the mass of the solute and converting that to moles using the molar mass. And we find that to be 0.2509 mole of strontium hydroxide. To find the volume of the solution, we need to find the mass of the solution and then convert that into a volume in liters. So our 30.52 grams of solute plus our 300.0 grams of solvent, which is water, gives us a solution mass of 330.52 grams of solution. Using the density of the solution, we can convert that mass of solution into volume of solution, which is 0.292 liters. And since we know our moles of solute and our liters of solution, we can now calculate our molarity, which is going to be 0.859 mole of solute per liter of solution. So now we're going to take all these values and do a chemical reaction using stoichiometry. So a student combines 500 milliliters of the dilute perchloric acid from the previous page, which had a molarity of 1.02 molar, with the strontium hydroxide solution we just made above, which has a molarity of 0.859 molar and a volume of 292 milliliters. We're going to start by writing out the balanced chemical equation for this neutralization reaction. When we say neutralization reaction, that's a term that we learned earlier in our reactions unit. It is a double replacement reaction between an acid and a base that makes water and an aqueous ionic compound. To balance the reaction, we had 2 hydroxides from the strontium hydroxide, so we had to put a 2 in front of the water to represent those 2 hydroxides. That means that we need 2 hydrogens from the acid, so we put a 2 in front of the acid as well, which then means there were 2 perchlorates, and look, strontium perchlorate has 2 as a subscript, so we are now all balanced. Remember, this reaction happens because you make liquid water. A double replacement reaction will happen if you make a solid precipitate, a gaseous product, or liquid water, which in this case, and all neutralization reactions, it occurs because of the liquid water being produced. Now we're going to do stoichiometry. We're going to say that the perchloric acid is the excess reactant and the strontium hydroxide is the limiting reactant. And we want to calculate what is the mass of water produced in this reaction. Since we know the strontium hydroxide is the limiting reactant, we're going to ignore the values for perchloric acid currently and just take our strontium hydroxide limiting reactant and do normal 4-step stoichiometry to get to our mass of water produced. In this particular problem, we're going to start with our volume of strontium hydroxide solution, which is 292 milliliters. We're going to use molarity to go from volume of a solution to mole of that substance, volume to mole. Then we'll use our mole ratio to go from mole of strontium hydroxide into mole of water. And then we'll use our molar mass to go from mole of water into gram of water produced. So we start with 292 milliliters of strontium hydroxide, where every 1,000 milliliters is 1 liter. And now that we have a liter unit, we know that every 1 liter of strontium hydroxide will be 0.859 mole of strontium hydroxide. We get that from our molarity. We can now use our mole ratio from the balanced chemical equation of 2 to 1 to go from every 1 mole of strontium hydroxide reacted will result in the production of 2 moles of water. And then using the molar mass of water of 18.02 grams, we can find out how many grams of water will be produced. And our final value is 9.04 grams of H2O were produced. Now we know that the perchloric acid was our excess reactant, but what we want to know is after this reaction, after we've used up some but not all the perchloric acid, how many moles of excess reactant are left over after the reaction? To solve this, we need to know 2 things. First off, how many moles of perchloric acid do we have before the reaction? Then second, how many moles of perchloric acid were used in the reaction? And then we can calculate the remaining moles of excess perchloric acid after the reaction. We can find the moles of perchloric acid before by taking the volume that we had, 500 milliliters, and using the molarity, that every 1 liter would have had 1.02 moles, to find that before the reaction we had 0.510 mole of perchloric acid. To find the moles of perchloric acid used in the reaction, we can take the mass of water that we produce. We know we made 9.04 grams of water, and just find out how many mole of perchloric acid would have to be used to make that water. So we go from grams of water into mole of water using the molar mass, And then we use the mole-to-mole ratio from the balanced chemical equation of 2 water per 2 perchloric acid to find that the moles of perchloric acid used in the reaction is 0.502 mole of HClO4 used. Find the difference between those two values, and you have how many mole of perchloric acid is excess or left over after the reaction. And our final wrinkle is to calculate the pH of the entire solution after the reaction. Well, in order to know that, we need to know the molarity of this perchloric acid after the reaction. The molarity of this solution will be the moles of our perchloric acid divided by the volume of the entire solution, not just the acid, the entire solution now, because we had 500 milliliters of acid, but then we added in 292 milliliters of base. We're going to assume that the total volume is just the sum of those two volumes that we combined, and that comes out to be 792 milliliters, which is 0.792 liters. Remember, molarity is moles of solute per liter of solution. We now find the molarity by taking our excess moles, 0.008 mole of perchloric acid, dividing it by the total volume of the entire solution, and we find that value to be 0.0101 mole per liter, which to find the pH of, we just take the negative log of that value, and we get a pH of 2.00 when rounded to 3 sig figs, which is still very acidic, but not nearly as acidic as our -1 pH that we started out with that concentrated solution.